Hello and welcome back. This video is going to be about structural design, and it's not going to be very precise. There's going to be a little bit of engineering in here, but mostly it's going to be sort of touchy-feely, go by rules of thumb sort of stuff. Alright, I think the first place we're going to start here is going to be getting the intake ducting sorted out, as well as the exhaust ducting, but the exhaust ducting is going to be probably a lot simpler. My main concern here is just we've got to make sure we leave enough space for all of the powertrain and avionics, while keeping a relatively straight shot from the intake into the fan face there. And then we also have to add that little deployable cheater door and figure out how we're going to actuate that. I think I'll just start with the exhaust tube, because that'll probably be the simplest to do. So it does appear centered. So then this should be radially symmetrical. I designed this little step, 3/16 step here, so that the foam board can slot inside the actual nozzle extension here. So this will be the actual surface we're going to, and it'll go all the way to the outside diameter of the fan, and we're going to add 3/16 of foam thickness to that. So then our thrust tube is going to look something like this. And that 3/16 will go to there. Just a simple conical tapered part. There we go. So that right there is our thrust tube. And actually, if you look at that, we're going to have to do some relieving cuts here sometime. Or actually, I think what will end up happening is that actually this outer surface will get relief cut to clearance fit here, or something like that. We'll have a bunch of formers in here that'll go around the ducting and support it once we figure out exactly what's going on here. Alright, so now it's time for the inlet ducting. This is going to be pretty fun to do. So the first thing I see is that this is our big battery right here, so we're going to have to stay to this side of it. So whatever that battery is doing, we're going to have to define a plane. So basically we're going to take this face straight back until the end of the battery. That's there we go. So there's our inlet face on one side. The thing is, I wonder what sort of area we're dealing with here in this cross section. Because if we add the thickness of the material here, I hope it's not too far below the fan swept area. Generally, when you're doing inlet ducting for ducted fans, you want to try and keep the area either expanding or constant if you can. You don't want to constrict it just to open it back up again, because if you do that, you're just making the air faster in the constricted area, which just gets you more frictional losses, more turbulence. Oh, there's something there, but this is just that area, right? So this is 3.36 inches squared, whereas this is... Oh, is that actually more? Really? That's actually more area. So that's good. So it's actually expanded past what it is up front, because the inlet has gotten taller. So that's good. Okay. So now after this battery here, we're going to start getting into the wings here, but I'm just going to ignore the wings for now. We're going to have to sort of integrate all of this stuff together. This plane is very tightly packed, so there's going to be a lot of intersection and stuff we're going to have to deal with, and everything's going to be real close together. So after here, well, now we have actually the top of the inlet surface. We could actually fill this stuff in. Something like that. So we're going to have some part back here that sort of tapers inward. Something like that. That'll allow the two streams to converge together. So that's our little inlet diverter thing there. So then the airflow is going to meet right here. So I'm thinking about how big I want this door to be. It's probably going to be fairly large, like about 6 inches long seems a good size, because what I'm concerned about is we want, since it's going to be hinged, we don't want the actual angle to be too big to get a lot of deflection, because that angle will induce flow separation from whatever flow is coming underneath in this direction and getting sucked up. We don't want this angle to be like super aggressive, or else it'll just separate in here. And so from this side of the inlet, there's basically just going to be one thickness of foam. So whatever is pulling from here is just going to probably get turbulent on the bottom anyways, but ideally it'd be a shallower angle. That also makes the surface bigger. So that makes the actuation requirements larger in terms of torque. But it also gives you a lot more airflow potential for that sheet or door. So instead of going through all this inlet, you could just come in from like here. Start it like right about here so we get right up close to that fan face. But whatever door we have, we don't want to run into this this nose cone here. So actually we're going to have to use that as our furthest forward point that we can use. I don't want it to get too close either, so we'll take this and we'll punch it out of the bottom. So here is that door, and this is what it's about, what it's going to look like actuating. So that's going to come up like that. Also, this door being here means that we can't have any spars or anything that would interfere with this. So let's just take a look again, and then it'll come up into the bottom of the wing where it'll be secured, and then it'll come back, probably cross under the fan, and then go back down to the other one. So it's going to be quite a complex bend there, but I think it's worth it for this this door here. And then we'll have a spar probably running like under the fan as well, so you can get all the deflection. There's a shorter path here to get into the fan inlet. I'm liking that. Yeah, that if we just take a look at that, that's pretty good access to the fan face there, I'd say. So the wings here, these aren't gonna have any of this actual wing thickness internally. They're just gonna be the bottom surface of the fuselage here. So essentially we're gonna have to intersect these with the rest of the fuselage. I'm gonna see if I can do that easily. So that'll be all the way down to here, I think. Yep. So that's what the actual wing skin is going to end up looking like. Now look at all that room for activities. So that's a nice open duct right into the fan face there. I'm thinking of what we could do next. I guess we could start splitting this fuselage up into the sort of lower inlet component there and this upper part of it. And then we'll have to do some work with the formers here and back behind the fan there. So now if we take this off, we can remove that separately from everything else, except for this part, which I forgot. That should be correct. All right. If we hide these, we can hide this and these and that. So our fuselage has been separated. I think we just need to focus on the this part back here. This will be fun. So maybe this is going to have to... We're going to have to separate this a bit here, because this guy is going to be about 3/16 from there, so that's not going to be a problem, but this thrust tube will be, so we're going to have to deal with that. I think we're just going to put one of these across here. We're just going to find where it interferes and then cut that part out of it. So take that, and then we cut that part out of it, and that'll make clearance for this thrust tube right here. All right, I think it's about time we put in our first former here. So we're going to hide this. So our first former is going to be on the fan. We're going to have the former backed up to these little tabs on the fan. So the plane the former is going to be in is in this plane right here. Then we're going to intersect this plane with these curves here, or these panels. There we go. So that gets us these lines right here, and that sort of subdivides this panel. Then what we can do is we can make this a surface, like this, or a face, and then we can take this and then offset the edge by 3/16. And so now that accounts for the thickness of the foam, and so this right here is the former. So we'll actually get rid of this outer line here. Now it's worth considering here that we offset it on all the sides, but there's no thickness of foam on the bottom here, since this actually butts up to the bottom of the wing, so we can re-add that 3/16 we took off in the bottom. And we can also intersect this with the fan here, and then get this out of there. And then that will be our former. And I think we'll actually double stack this, so we'll go 3/16 there, another 3/16. Select all of that, make that a group. Alright. You'll see that we have a former that will follow the contour of our fuselage with a 3/16 in between it for foam. It meets perfectly with the bottom here, and it has the perfect contour for the fan to hold it in place. So with this here, we can also add a former probably right before the end of the thrust tube. And make that a group. So that's our second former there. So we got one holding the fan, one holding the back of the fan there. As far as the rest of this, I don't think we really have any formers to deal with because none of this can really have any formers because it's essentially just the inlet surface. So we can't add any formers in here or else we'd have to add another wall to it. So now we can move on to this one. There's going to be a bit more detailed former work up in the front here. Actually, let's start on this first. I think I already have formers and stuff in here, do I? Or I don't have the cross sections in. Okay. Well, we'll deal with this first. That is the former we need right there. And then we could offset to this to both sides, just like we did with the other ones. And with these, you could just make one and then have it overlap on both sides, but that only leaves you a very small overlap. So typically I like having the double former like this so that there's more of a ledge there for you to wrap your sheeting onto, basically. Another thing with this sort of hatch design is that I'd like to have something to keep this radius and this arc here in place as well, so I'm actually going to use this as a former. And I'm going to do that on the back as well, but we'll use both of these as formers. And this one, since the angle here is quite severe, you can see from vertical, whereas this one it's not as severe. There's going to be a lot of trimming and beveling that has to be done on this surface down here to get it to fit up at the nose here because of that 3/16 that's going to come up like that. Basically, you're going to have to bevel that part. And then we can actually keep these two as the same part and just fold it over when we're done. We might actually do something similar here and have sort of an insert on this piece. And then that would make it, because there's not much up here, the nose wheel's behind that. So this will be probably the GPS and the pitot sensor up here. So we should be able to sneak that in through the back. And then this surface and this surface will make it easy to embed magnets in here to stick the hatch on. So maybe it slots in like above the battery here. There's some sort of slot or something that it, or a tab that fits under the back, and then the magnet holds it down at front. That's a potential method of hatch retention. So again, we're just going to be making formers here. This one right here, I'm thinking we could actually combine these two into a single former, just like we did with the canopy piece up there. So that about covers it for the formers, at least in the front part here. Now we got to start thinking about this here nose wheel and how that's going to work. So I actually have the nose wheel. I'm going to go and get some dimensions off of it. 1 1/4 between the bottom of this and then the top of the other one. And then it's going to come up just like a little bit more. And then it's going to extend back, and that's going to allow the servo to do its servo thing and steer this. It'll be a servo here with an arm that will link into this, and then the arm will keep this from moving side to side. That's basically how the nose wheel mechanism works there. Now we can also start thinking about the Canard stuff here. There's going to be supports for the Canards that are going to go on the outside, or they're probably going to be embedded into the foam on this side piece here. It's going to be a steel wire that's probably going to be in some sort of shape like this that'll go between the two. It's going to be, this wire is going to be embedded like in the middle of this foam or maybe towards the bottom of the intake, and then because it's going to be glued into the Canards like this on the underside. And then I'm going to use servo horns, just like I'm doing with the nose gear, to attach the Canards to this, basically support them right at this point here. And then they're going to go across, because you'll have basically a bearing there and a bearing there, so it'll be constrained good. I think about side-to-side constraint. But, and then in the middle here, I'm going to have some sort of, maybe a bend in the wire that I can get a control horn on or something, and then there's going to be a servo basically with a linkage set up to that. And that should be able to move both canards for pitch control. That's the idea anyway. So that servo is going to need a platform on it. The axis is probably going to be somewhere around here. So then the servo mount could just be an extension of this, and that would make everything simpler structurally. Probably about there looks good. Now beyond that, we have the battery tray. This is going to be interesting. Now I could just have it rest on the bottom of the fuselage, but I think we probably want something to hold it up off the bottom there. I think we'll probably move it like here-ish. That's reasonably close to the top, but not too much where it's going to hit. We got like half an inch maybe? Yeah, half an inch. Yeah, I'll move it down like like an eighth. That'll be good. Alright, so now let's pick up this bottom reference plane here. And then there's that former that automatically got generated there. Up, extrude that along. All the way to here. That's that. Alright. So that's what that rear former looks like. And now we can start working on the formers here. Go and make components, or make group. Do that for here as well. And for this very last one, I'm not sure what we're going to have to do here, because this is how high? 5/16. This is a square section anyway, so I'm not too concerned about. This former won't do much. In fact, I'll probably keep it open so that I can get a push rod through there for this pitch mechanism of the thrust vectoring. And I think, actually, that this part of the fuselage is done. I guess next we'll focus on the vertical stabilizer here and integrating that into the rest of the structure. So first let's consider what's underneath this, because yeah, it's going to be doing some weird stuff here. If you can, you want to minimize the length of your load path. So for the rudder, I'd rather go to this if I can, because this is like the main fuselage, and then it gets to the CG through this main fuselage, instead of going through the rudder and then this thing and then from this thing to the main fuselage. So for this, we're going to want to extend this part down, offset that again, reverse faces. All right, so that is our rudder ready to interface with the rest of the structure of the aircraft there. So now if we unhide this, we're going to cut a slot in this so that the rudder will pass through. So now you can see how this is just going to slot down just like that. Next, we're going to look at the front of the fuselage here and how it interacts with the landing gear. I think we're going to have a cutout here for nose wheel, just so it can do nose wheel things. So we'll erase that. And then I'm not going to model it, but I'll have some sort of small foam thing that keeps the nose wheel separate from the rest of the aircraft. I'll just do that when I'm building it. And then I'm thinking, because this also needs room to pivot side to side, I'll cut that out as well when the aircraft's fully assembled, and I can get an idea of the clearances and all the angles and stuff it needs. So that'll just stay there temporarily. I can't use the offset tool on this face because it's curved, but if I could, that's essentially what it would end up being. You would have basically a perimeter around here. There'd be a little triangle sort of wedge shape in here. We'll do that once we get to the sort of unwrapping stage of everything. So I think it's about time we get started on the wings, because there's not much left to do here. So the one thing I see right away for the wings is that we're going to have to punch out some holes for the main landing gear here. There we go. And then we'll punch that out. Sort of feel like making it an eighth each side, because my tolerances aren't going to be crazy good on the the lateral positioning of that landing gear, so if we can get a bit of extra wiggle room, it wouldn't hurt. Let's see, we already got the door cut out of there, so we're definitely going to need some formers in the wing here. I think we might be able to have this part of the wing actually slot into the side of the fuselage. That would be cool. And we'll put a bunch of slots and everything in the fuselage just to make assembly easier. I mean, you could make a rib that would go from the back here all the way to the front and have like this weird angle stuff going on, but I'd rather just have a rib that is straight relative to the rest of the aircraft, and that'll make it a good bit easier to construct. So the first thing I want to do is sort of get a rib in there, and I think we can do that. A convenient place to do that would be just on the other side of this landing gear right here. So right on that pocket, and that would form one side of the wheel well conveniently. So that's our wing rib. Make that a group, and then we can extrude it this direction. Now I'm not going to be trying to make this control surface like the wedge that it is here. I'm just going to have the top surface of the wing, so this control surface is actually going to end up looking basically like that without this bottom part here. So this point where it meets here, this is 3/16 from the top, and then there's this little bit here, and then there's 3/16 from the bottom. This little gap here is going to get filled by basically just glue along the trailing edge. On some of flight test models, they have sort of a bigger air gap here down below their elevon or their aileron, but that's not the best for drag, so I try and keep this distance here minimal. So if we take the actual position that that rib is at, and we go to the wingtip, how far do we have? So 9 5/8. So we could put a rib like every 3 inches, seems all right, and we'll get like 2 more ribs in there. Actually, I think I might want to figure out where I have to start undercutting, or cutting the bottom of the wing, because once I do that, I can't put ribs in it. So, because I want to get that wing rib to end somewhere around here. So maybe we don't do 3-inch spacing, maybe we do 1.5. So if we add 3/4 to each rib spacing, actually less because there's going to be a foam thickness. So we'll do 1/16 shy of 3/4 added to 3. So that would be 3 11/16. Cool. And you can see here on this final rib, there's pretty much 0 thickness to this actual rib. So it's just a little nub in there. Oh, also another thing with these is that you want to extend them all the way back to the rear of the wing. And then this one, you could actually almost leave this just completely out, and it would probably be fine, but I think I'm going to leave this one out, and then this will become the cut plane for transitioning from a regular wing to an undercut wing, sort of like the flight test style. And then for this part, we're going to essentially take off this part of the wing skin below the leading edge here. So we're just going to erase that. And so with that done, we can start to think about the spars that are going to go in this wing. So with your wings, your lift distribution is probably going to look something like this blue curve. It's going to be elliptical if your wing is designed to have an elliptical wing distribution, or it's going to look, you know, something where it has less at the tips and more at the root. If your wing has any taper and it's not negatively tapered, so it has, more chord at the root of the wing than at the tip, it's probably going to have a shape that's like this. A natural Hershey bar, just rectangle shaped wing will have a lift distribution across it that looks like this, because it has wingtip vortices, which actually reduce the angle of attack naturally of the wingtips, and so they generate less lift. For the sake of structural analysis, we're going to be making a simplification, and that's, we're going to assume that the load is distributed as it is in the red arrows instead of the blue arrows here. So the blue is closer to the real world, and the red is our assumption. And this is actually going to be a conservative estimate, because if you were to think about the sum of the force on both of the distributions, they would be the same. But the red force, if you were to sum it, it would act actually further out than the blue one would. So you're actually overestimating the load that you would have to carry. And if you were to sum this basically constant load into a force, it would act at half of the wing span of that one particular wing out from the span. Essentially, you could collapse all of this distributed force that we're assuming is just constant along the entire span into a single force that acts at half of the span. And then you can use that with the distance to find the moment around the center of the spar, and that moment will be the maximum bending moment that the spar will experience. So the question is, what is this load and what is this distance? So the distance is pretty simple based on what model you have. In our case, let's take a look. I'm going to do my analysis in metric units. You'll see why in a second, because it makes everything a little bit easier, although it still is a bit difficult. So 6.5 inches times our 2.54 centimeters. So that's 16.5 centimeters. And then what load are we trying to support? Well, we know that each wing supports, well, in steady level flight, each wing supports half of the aircraft's weight. So what's the weight of the aircraft? Well, current projections have mine at about 1,650 grams. So if we take a calculator, so that's 1.65 kilograms, and then you would multiply that by 9.81 newtons per meter second squared. You get that the aircraft weighs about 16.2 newtons, but then you divide that by 2. So then each wing in steady level flight would support 8.1 newtons worth of force. But the aircraft's time is not spent all at steady level flight. For it to fly and to do turns and to take off and land, it has to be able to pull more than 1 G. So this number here, this weight, will actually get multiplied by the load factor of the aircraft. So the load factor is basically how many G's you're pulling. So depending on what type of aircraft you're building, you can change this so that you'll design the spar to different design loads essentially. For something like a big glider, like a solar plane or like a soaring plane, that's not doing any crazy maneuvers, that's not dealing with huge gust loads, it's flying pretty slow, you probably get away with designing for like 2.5 G if you're not doing any crazy turns or stuff like that. If you're like a normal aircraft, you know, you're doing a bit of hot dogging around the sky, a bit of maneuvering, maybe dealing with a bit of gusting. If you have landing gear stuff mounted to your wings like I do, you're probably going to want a bit more margin for that just because they'll be pushing up on the wing structure. Funny enough, if you have like engines on the wing or wingtip pods, those actually act against the lift, and so it decreases the maximum bending load. But if you have landing gear or stuff like that, maybe you design to like 5G. If you're doing like crazy maneuvers and stuff, and you've got like a ton of control authority and you're flying really, really fast so you can get a lot of dynamic pressure, maybe design for like 10G. And then on top of that, you want to add some sort of factor of safety to factor in the uncertainties in the analysis methods and your material properties, for example, all that stuff. So typically in aerospace, factor of safety is like 1.5, maybe 2. In spaceflight, it can be lower, like 1.25 to, I think on commercial crew missions, it's around 1.4. And basically, the lower factor of safety you can get away with, the better, because it means you're carrying less mass, but it also means the less margin you have on top of your design load. So for what I'm doing, this aircraft is probably going to fly, it might not be my fastest, but I'm expecting at least 80 miles an hour out of it, so I'm going to be able to get a good bit of lift out of it. So I'm going to choose 10G as my ultimate target. So that's going to be 81 newtons. And so realistically, with the Efflux Mk, I think the highest I saw was around 6G. With the Mark 1, it was around 5G. So I don't think I'm going to be pulling anywhere near 10G with this. But in the event that I do, I want to make sure that my spar is like reasonably acceptable to do that. And so if you multiply those two together, it's going to be 13.36, call it 13.37 Newton meters. So that's the moment the spar has to react, and that's the big M up in this equation here. So now this here sigma is actually the maximum stress of the material, and this is determined by the material properties of the material. So in a spar in pure bending, you're going to have tension and compression forces. So you want to choose this sigma as the lower of the two forces, essentially. I should say that this analysis also assumes that the failure mode of the spar will be in bending, and that it will be due to axial forces within the spar. If it's something like a uniaxial carbon fiber rod, like a carbon fiber rod with all of the fibers running in the same direction, those can fail in shear between the actual fibers. The shear forces will build up, and then it'll tend to fail a good while before you start actually breaking fibers or crushing them. So keep that in mind, especially with composites, because composites are highly non-isotropic. They're anisotropic. Whereas with something like metal, the tensile stress and the compressive stress are going to be fairly similar. Doing this analysis with composites and expecting it to work is not a good idea generally. But we're going to do it anyways, just for sake of argument. This analysis also assumes, by the way, that the spar is the only thing carrying the load, whereas actually the skin of the wing, in this case, will actually carry a good bit of the load. So for example, if you look up the ultimate compression strength of carbon fiber, it's around, it says 1 to 3 gigapascals, which is huge, whereas the actual epoxy that binds it together is way below that, like at least an order of magnitude. So for the purposes of this analysis, we're just going to assume compressive stress of 50 megapascals, and a pascal is 1 Newton per meter squared. So then what's I? This is something that's called the cross-sectional area moment of inertia of the actual cross-section you're using. So basically it's a measure of how effective the actual cross-section is. If you imagine we had a rectangle like this, right? That's not a rectangle, let's change this. If you imagine we had a rectangle like this and we applied a load on it from the top, it would be a lot more resistant to bending than if we applied that same load to it like this. And that's because this sort of cross-sectional shape, when loaded like this, is a lot more effective than it is like this. And that's because there's more material farther away from what we call the neutral axis, or the line of zero compressive or tensile stress in the actual material. Because when a material is loaded in pure bending, you could sort of imagine that if I were to have a force pushing down on this, and say the beam extends out this way. What's going to happen is this top part of the beam right here is going to want to stretch out, so it's going to want to go this way. The bottom part is going to want to compress, it's going to want to go this way. So inside the material, if you took a look at it, it would have compressive stress on the bottom and then tensile stress at the top. Line where those two met and where there was zero compressive or tensile stress in it is called the neutral axis. And for pure bending loads where there's no shear or anything involved, that neutral axis is actually going to be in the sort of geometric center of the cross sections. And that distance from the neutral axis determines actually the magnitude of stress. Because the material is elastic, you could sort of do a Hooke's law sort of analysis and say the farther you are away per, say, a unit of deflection, angular deflection in the material, the farther you are away is directly linearly proportional to how much stress you have. That's sort of the classic Hooke's law example of like the material acting as a spring. So what that means is that this stress here is directly proportional to y here, and this y is that distance from the neutral axis to wherever you're measuring the stress. Now we're concerned about the maximum stress, so we're going to want to measure that distance at its maximum. And so there's lots of ways online to figure out the cross-section moment of inertia of whatever your particular shape is. There's calculators for non-standard shapes. There's ways that you can add shapes and subtract shapes. It all comes down to like a bunch of integrals and calculus and stuff, but it's not too hard once you get the hang of it. The moment area of inertia is pi times the radius to the 4th power divided by 4 for a circle, and then for a hollow circle you see you just subtract the difference between the radii here. But this is the moment area of inertia. You can see pi diameter to the 4th over 64. That's the same as radius to the 4th over 4. So the carbon fiber spars I have are 7.5 millimeters in diameter, and they are 0.5 millimeter wall thick. Multiply that by pi, and then divide that by 4. So actually it's 0.675. 0.675. Actually we call that 6.75 times 10 to the minus 11 meters to the 4th. All right. So now that we know these values, we can go ahead and calculate the stress for this given bending load and the length there. So onto that carbon fiber rod, the epoxy in it would probably just break out of it, and then it would fail somehow. But I could tell you that I have these rods in hand here, and I could feel that they're plenty stiff for what they need to do. They're not, I mean, super stiff, but we have multiple of them, and it's sort of a touchy-feeling thing, but I mean, if you can get this to work out good, then whatever you do in here will definitely work out good. If it looks good and the math says it'll work and it feels good, it'll probably work. This is not the most accurate analysis because, again, the skin of the aircraft does a lot more, especially on these foam board builds, than you actually expect. And that's how Flight Test is able to get away with making spars out of foam, just by getting enough separation, like we were saying, distance from the neutral axis, getting enough separation from the neutral axis so that it can handle those high bending loads. So now we have the task of putting the spars in this thing. First, let's find where that fan is, because that's going to be in our way. So something about wings is that they generate most of their lift actually towards the front of the wing. So if you had a wing like this, just a rectangular wing, and the airflow was coming at it from this direction, the center of lift of the wing would actually be around a quarter of the way back from the front of the wing there. So the lift, if you were to consider it as a force, and the wing had an airfoil shape that went like, you know, up like this, if you're going to integrate all of the lift over this entire wing, it would act at this quarter chord line. And that's pretty true for most wings. If you're thinking about the load on this wing and where to put the spar so that it would be on that quarter chord so it could be structurally efficient, it gets a bit hard with delta wings, but if you sort of do it so that like approximately a quarter of the area is in front and approximately 3/4 is in the rear, you're going to be pretty close. So looking at this, I mean, it would be nice if we could put our spar like right here, but the landing gear's in the way, and we can't put it in front because we have the door. So the only places we could really put it is up here where there's no wing, so there's not really a good point to putting it there, or we could put it like right under the fan. So I think that's probably going to be where we end up putting it. We have a bunch of spars, so maybe we could put like one here, then we could put one like across here too. Like, we don't have to keep them all in one space, but just considering the actual lift force that's acting, it would make sense to put most of them here, around here if we could, but we can't, so we put most of them here. So it's pretty much 5/16. Anything that's 5/16 or greater, this thing will fit in. So what's the thickness here? About 7/16. Okay, so it'll still fit in at least to the second rib here. And beyond that, I think the foam board, based on my intuition, should do a pretty good job of keeping the wing from bending. So if we can poke it out just a little bit beyond the second rib, I think we'll be good. I think we'll sort of put 2 main spars under the fan, and then we'll put, oh, that's another thing. Are we going to have space under the fan? Let's see, because we only have 3/16 there, right? Yeah, we only have 3/16, not 7/16. This is what happens when everything gets packed so tight, is that it's just hard to fit stuff. Because we can't move this thing up anymore, because then it would just hit the top of everything, and this would start coming out of the top of the aircraft. What's the furthest back we could put one of these, really? Like, is this 5/16? That's about 5/16. Right there, actually. So this is probably the perfect place to put that other spar, and then as the wing decreases in thickness as it comes out, and it sort of tapers to the back here, yeah, we could have an auxiliary spar in the back that, or maybe we run these at angles, actually. Something like that. And then we have some sort of spar that goes behind it that'll triangulate, or not triangulate the load, but because there's no join between the spars, spar this way that'll take the load within the wing, and then one to take it across the 2 wings, I guess, or maybe multiple behind here. I mean, I don't quite like the idea of putting something in the airflow here, but I think if it's necessary, like having like a little 1/8" lip or something in front of the fan is not really going to matter, especially if we have the bell mouth on. And if anything, we might be able to sort of feather that into this ledge here and get a bit more of a radius going into the intake, so that might help when the doors open. We'll take it 8 inches out each side, call it good. I think we said we wanted one behind the fan too, so I'm going to try and find a good spot for that. Put that like around here-ish would be good. Offset this out. And that's going to be, yeah, it's going to come to around the same distance, I think. And then we'll go all the way back to center line. It'll poke into the thrust tube a little bit, but that's fine by me. We'll just have to clearance the thrust tube a little bit. So I'm wondering if we could get some sort of sideways bit in here. And I think right about there, just call it good. So that's going to be the main structure inside our wing there. One of the last things we have to do here is just to figure out where the main landing gear wire is going to go. So it's probably going to come out of here. And the wire I'm going to be using is an 1/8 inch thick, so we'll just add an 1/8 inch there, and that'll add some spacing for the wheels, sort of side to side. It's going to come up into here, probably like that, and then it's going to go maybe an 1/8 of an inch up into the foam, sort of back up to the spar. There's probably going to be some sort of sheet that'll go on top of this and cover it, and then blend that into the spar just so we get sort of a nice inlet lip here. And so that'll be the main landing gear that we have to bend up, and I'll just copy that to the other side. So now, as far as I know, I think that's it for structural design. I think everything is there that we need. All the widths of the foam and stuff is accounted for. All of the skins and formers work out. So to make this go together easier, and for some of the structural or sort of shape holding of the wing around the wing root, we're going to end up using some tabs here just to make everything go together easy. You could align all of this by hand and get it like exactly perfect, but if you have registering tabs that keep the parts oriented with respect to other parts properly, that can make it a lot easier to assemble everything because it'll just slot together like Lego. Now you could put some of those on the landing gear fairing bits here, but I don't think those will be necessary since I can position these pretty much by eye after the landing gear and stuff is installed. They're not super critical to anything, so I'm not going to bother with tabs on those. But where I am going to is some of the fuselage stuff here. So, and then for tabs, you could go full depth of the foam, 3/16. I think we're going to keep it to an 1/8 of an inch. A 1/16 is probably too small, but you don't want so much, or at least I don't want so much that it's going to poke out. You're going to be able to see it on the other side. I want to be able to have everything look relatively clean, because with this technique you do risk disturbing the other side of the foam when you sort of gouge out that little slot there. And so I think we'll do 1/2 inch by 1/8 inch slots here. We can go back into our fuselage here, and then we could actually pick up the location of those tabs right here, and right here, and right here, and then right here. We can just bring those down the width of the foam, which is 3/16. And of course we can copy this to the other side. So after these two pieces, these fuselage pieces are going to continue under this sort of ridge back here, so we don't need to worry about slots in these pieces, but we do need to worry about slots in these pieces. So this top part is actually going to slot down into this bottom part. Copy those to the other side, and we can add these onto the formers as well. So then we can transfer these into these pieces. Next we can work on these pieces into the bottom plate, and of course this former here. So now we can focus on this guy into the bottom of the wings here, and we'll copy that to the other side. So since those tabs are only 1/8 of an inch, when we go to transfer these to the wings, you'll see they actually come short of where we need them to be. Actually, I'm thinking about it here. I don't think we need a tab here really, because this is going to be sort of visible on this portion of it. I'd rather have some sort of overlap going on there than this. So this part right here is going to be folded like this. Then the rest of these on the inside, we've just got to project those down to the surface of the wing. So there's that for the bottom of the wing done. Now the final tabbed interface we have is going to be between the wings and the actual fuselage itself. With this we're going to need a bit more tabs than usual, just because we're trying to hold the shape of the wing here, so I'll try and get them on a reasonably close to regular spacing. Alright, so now we'll transfer those over to the fuselage here. I'll count 6. 2, 3, 4, 5, 6. Perfect. And there we go. So now we'll just copy that to the other side. And we'll copy the wing to the other side. And that's it. The structural design for this aircraft is done.